Okay, good morning everyone. So I just wanted to do a small demonstration about ChemCompute. So I'm logged on to ChemCompute. If you don't have a login, you can make a login. It's free. And I suggest everyone just use the Google, the site.pdn.ac.lk Google login, or you can make a login just using the email, and there can you please use the username as the first part of your Google address. Okay, so what I'm going to demonstrate here is how you can submit a PSI4 job. So first you can just go to this games/PSI4, and then we can go to submit a job, and then it will take you to this screen where you have the user interface where you can generate and draw molecules. So we're going to actually do this. You can also search or load an input, but we're just going to start from scratch. So to start off with, let's just draw a very simple molecule. I'm going to draw ethane, and then let's put just another functional group. Maybe let's put not that. Let's go back over here. Back. And there we go. Okay. So this we have ethanol. So you can draw any molecule that you like, but please remember that with quantum calculations, the larger the molecule, the longer it will take. So once you finish drawing this, you can click on this button to transfer. Make sure that you have the automatically optimized and hide regions automatically clicked, and then after that you can click transfer, and once it transfers here, it will optimize. And this optimization is not a quantum mechanical optimization, it's a molecular mechanics optimization. And what it will do, it will try and it will change the conformer to get you a local minimum, and it will also try and get the proper symmetry of the molecule, because symmetry is very important in quantum calculations. It can reduce the computational cost quite a lot. So now it's finished optimizing and then finding the symmetry, and it will show the symmetry group that it has found here. And once this has, you can actually optimize a few times. If you feel like that the molecule has not been optimized, you can optimize a few times, and then once you're happy with the structure, you can click on this next. Okay, so this will take you to the parameters for the quantum mechanical calculation. So here you can select which code that you're going to use, games or PSI4. Both of these are open source codes. You can install them on your own machine, but these are installed on the ChemCompute server. So for now, we're just going to stick to the PSI4. Either of these is fine. I'm just going to use PSI4 because they've set it up in a nicer way in ChemCompute. Then you can give a name for your input file. So I'm just going to use the name of the molecule. So I can say ethanol, and then I'll say the one in case lots of people have run ethanol. No need of comments, and then you choose the charge. Molecule is neutral, so charge is 0. And it is in a singlet state, so the spin multiplicity is 1. Right, next you need to choose the type of calculation that you're doing. So a single point energy is going to take the coordinates from this structure, and it's going to run the quantum mechanical calculation using those exact coordinates. However, what we're going to do is we're going to run a geometry optimization. That is, you're going to take these coordinates as the starting point, and you're going to calculate the code is going to calculate the energy of this molecule. It's also going to calculate how it needs to move the atoms, right? In which direction it needs to move the atoms to lower the energy, right? And it's going to go through a few rounds of moving these atoms around to get a lower and lower energy, and that is what geometry optimization is. Right, so we'll choose this geometry optimization, and then the next set of parameters that you can choose from are the add-ons. And here you can choose whether you want to get the thermodynamics, the UV visible spectra, the natural bond order, or the IR. You can also choose none if you want to just quickly get the calculation done. For now, let's just keep this IR chosen, and feel free to just play around with these and run it again and see what information that you get. Next, we move on to the basis set. I will put some more information or documents on what basis sets are and why they're important and why it's important to choose the proper basis set. For now, we'll choose historically a very widely used basis set. This is a 631G star basis set. Okay, next, the molecular orbital method. You can use the restricted Hartree Fock, and then next is whether we are going to use ab initio or we're going to use density functional. And we can actually use a density functional. It's actually much quicker than just pure ab initio. Now here you are not necessarily calculating the same thing as a pure Hartree Fock calculation, but you're calculating the electron density for each molecular orbital. Okay, so for now we'll choose the B3 lip. For the solvation method, you can choose none. For the computer cluster, that you can choose any one of these, it doesn't matter. For the processor cores, choose one. This is good enough for a small molecule. And for the memory, the 2 GB is the only option I have. And for the time limit, you can choose 1 hour, that is fine. Okay, so once you've chosen these parameters, you can just go ahead and submit a job. And what will happen is it will calculate the input file, and it will send that input file along with the commands to run this job to the server. And the server will actually start running the job, and this will give you just some output. And here what's happening is it's running the self-consistent field so these iterations are showing you the self-consistent field iterations, and then once it finishes that iteration, that means it's calculated the energy for that particular configurations of atoms, or those positions of atoms. Then it will change the position of the atoms a little bit and then do another FCF calculation there. So this will take some time, so let me stop the screencast, and I'll put another screencast once we get the job completed and about analyzing the results.